Okay, we're going to talk about exponential and logistic functions. The homework's going to mainly focus on exponential. Logistic is not something I'm going to really test you over, but it's interesting. It does have some real-world application that we should look at just for the sake of having a conversation about math. Okay, so you'll learn about exponential functions in the graph, the natural number e, some logistics, and some real-world population models. These do exist in the real world, including populations and other applications in finance as well. We'll see. So exponential functions have this form, y equals ab to the x. That's on our formula sheet. That's really important. That's the most basic form. You're going to see we're going to manipulate this a ton throughout the homework, where we're going to change the base, for example. But this is our general form of our exponential functions. And it's really simple, you know. If you're basically starting with some a and you're multiplying by b a specific number of times. So there's the function, you know, it's a, b to the however many times you're multiplying b by. So you can see it's just continual multiplication by something each time. So if the population doubles, then b would be 2. And you're just, you know, if it doubles every year, then after 4 years, there would be the equation right there. If you start with 100 and it doubles after 4 years, what would the population be? Well, that would be the expression. So if you start with 100 and it doubles after 4 years, that would be the expression. So it's pretty simple to see where this comes from. If the population cuts in half, then you can see the growth rate is declining. And this would be 1/2. So after 4 years, if the population cuts in half every year, this would be the function. Now the book gives this, which is a little confusing, but I just kind of explained it. Basically, you take one term, you multiply by b to get the next term. That's what I just described. That's how the book says it. And then, you know, keep in mind that b, if it's less than 1, is decreasing, and if b is greater than 1, it's increasing, which I just described. So we're going to have exponential growth and exponential decay. So basically, if b is greater than 1, it's going to go up as exponential growth. If b is less than 1, then it's going to go down as exponential decay. So let's take a look at an example then. This is 2 to the x minus 1. Let's look at the parent function. We know the parent function, if you plug in 0, it goes through 1. So the parent function goes up like that. If we then subtract 1 from x, we know that moves it to the right, so we know it's going to shift it 1 unit to the right. So it's going to go through this point now, 1, 1. But other than that, it's the same. Now, if we do 2 to the negative x, we know that if we change the sign on x, it reflects it over the y-axis. So whereas the function went like this, now it's going to go like this. And another way to look at that is the fact that 2 to the negative x is really 2 to the negative 1. So I can really make this 1 over 2 to the first power, make that exponent positive. So if I change that so that now you can see that this is y equals ab to the x, where a is 1, b is 1/2, that's exponential decay. And so now it's going to go down like this. So that's another way to look at it. And then the last one, we have this 3 that we're multiplying. We know that's a vertical stretch. So we know that whereas once this went through 1, now if we plug in 0, this goes through 3. So we know that it's basically stretched vertically more than what the original parent function was. Now the natural number e is something you need to know. You don't need to know this necessarily, but it's basically if you take 1 plus 1 over x and raise it to the x power, and as x gets bigger, this number right here approaches this natural number e, which is 2.71828, and it goes on forever. It's an irrational number, it never repeats, just like pi. Now, this number appears all over the place, and like I said, in population, in finance. It makes us think that this is one of the many things that make us think that we're discovering math and not just inventing its own language, because this number exists in nature, essentially, and we've discovered it. So basically then, if we have y equals ab to the x, we can replace that b with e to the k then, if we're going to do continuous compounding. So this is really the same thing, because if you compare, b is really equal to e to the k. So we're going to have situations where we can say, okay, well, let's make b equal to e to the k, as you see in the homework. And we can find out what k is then, that would make that equal. So if b is 2, we can find out what k is then, just by taking the natural log of both sides. And we know what that brings the exponent down. Natural log of e is 1, So k equals the natural log of 2. All right, so we'll practice that in the homework. So just looking at another example of transformations then, if we plug in 0, we know this goes through 0, 1 again, exponential growth. That's really just 2.71-ish, to the x. So if we add 2 to that, we know it moves it 2 to the left. So we would just move it 2 to the left, and we now go through negative 2, 1. If we change the sign on y, we know that reflects it over the x-axis. So this would just go down here, like this. And then if we subtract 1, we know that just shifts it down 1. So it would just now go through the origin, and the asymptote would be the line y equals negative 1. So then logistics functions, I won't test you over this, but they're interesting. You take a number divided by 1 plus our exponential function, which we can write 2 different ways, and it gives you this logistic function which looks like this. Now that's perfect for population growth because c is our limit to growth, and we know that populations start off small and grow exponentially, but eventually they run out of resources, there's some constraints on their environment, whatever it is, and the population levels off. So we know that population doesn't really grow exponentially because there's not enough resources, right? So this works perfect for population growth. It'd be great to do some application problems, which hopefully I'll be able to find some for us with this function. But other than that, it's not something I'm really going to test you over. All right, we can look at one example here. This says, based on the recent census data, a logistic model for the population of Dallas 2 years after 1900 is this. According to the model, when was the population 1 million? So basically all we have to do is plug in 1 million for P and just solve. Now I know this is a lot of work, but we're going to have to multiply both sides by this number. So we have 1 million times 1 plus 21.602 e to the negative 0.05054 t equals 1,301,642. Okay, divide both sides by a million. All right, it gets rid of the million from over here. We have 1 plus 21.602 e to the negative 0.05054 t. And this side that gives us, just move the decimal place back 6, so 1.301642. Subtract 1 from both sides. 21.602 e to the negative 0.05054 t equals 0.301642. Divide both sides by 21.602. And then take the natural log of both sides, and that gets rid of the e. So you have negative 0.05054 t equals natural log of this number, which is about 0.01396, and divided by negative 0.05054. And that gives you the t, which is 84.5 years. And we know that's the number of years after 1900. So that'd be 1984 and a half, so 1985 is when the population reaches 1 million. Okay, we'll practice some homework problems now.